time for
chemistry.
Yeah, baby.
I can't handle the stress no more, dog. These damn A levels.
Hello, folks. Oh, that's a bit big. Turn that down. For all my days, I need to sort my lights out. It's like there's a ghoul on the camera. Okay, right. What's happening? Okay. A little bit of chemistry. So just doing some real, because only doing an hour, so just going through some pH and weak acids, and that. There's obviously a lot more to this topic, but we'll go through a bit of this. So yeah, we'll get into this. How to calculate pH and weak acids. This is part of physical chemistry. So if you like your maths and your Kc and your Kp, it follows quite similar rules, weak acids, because it's Ka, it's another constant. All right, let's get into it. So hope you guys are all good, and let's go through some of this stuff. So let's go.
Stick around.
I'm gonna have to science the shit out of this.
All right. Okay, so straight off the bat, what do we have here? So pH. What is pH? Well, if you're ever asked to describe what pH is, it's the minus log of the hydrogen ion concentration. And one thing that I've noticed on this little PowerPoint is, bloops, I've got, oh, that's better. Well, not much better, eh? Oh, that's better like that. Yeah, you should use square brackets. Believe it or not, in your exam, if you use rounded brackets, you won't get the mark, because square brackets are for concentration and rounded brackets is pressure. So if you use curved brackets, that's pressure. Square brackets is for conc. So use the formula to calculate the pH of the following solutions. Well, I've only got one here, so 0.01 mole per decimeter. You're going to need your scientific calculator, and you're going to need to be able to press the minus button and your log button, depending on your calculator. And that's all you've got to do. Minus log, put whatever the hydrogen ion concentration is, press equals, and you'll get the answer. So see if you can do that one right there. So what you're looking to do on your calculator, if you haven't got one, you need to grab it, because you'll need it if you're going to do the questions in today's lesson. So you're just going to press minus on your calculator, then you're going to press the log button, and then if the hydrogen ion concentration is 0.01, you're literally going to put in 0.01 and then press equals, and you will get the correct pH. So minus log 0.01, and you should get a pH of 2. Okay, coolio. Is everybody all right with that? Everybody know how to do that basic stuff? Hopefully you do. Well, we shall do the opposite. So we shall do the opposite of that. That's a very good question. So that is what we're going to do next. So bish, bash, bosh. We have that right over here. So calculate the concentration of hydrogen ions in mole per decimeter in a solution with a pH of 9.43. So what you need to do now, that is what I did to get the first answer to the first question. We're going to do the reverse of this. So we have the pH and we want to turn it back into the hydrogen ion concentration. So what you're going to do now on my calculator, which is some crusty ass FX85ES. This is from the 1970s or something. But I'm going to press Shift Log. So you press the Shift on most calculators. You press Shift and then Log. So you're doing kind of like the negative log or whatever it is. And then you're just going to put in the pH. That's right, Matilda. Yeah. So you're going to go like that. What you really want to do, forgotten how to speak. I'm just going to press Shift Log. Let's do that right now. Shift Log. And on my calculator, when I press Shift Log, everyone's calculator is slightly different. Some people get the little box up there. My crusty calculator does a little arrow and then a bracket, and then I'm going to put minus 9.43. 0.43. The minus is key. If you try it without the minus, you'll see you get a completely different answer. So I'm going to put minus 9.43 equals, and yeah, absolutement, I get 3.71 times 10 to the minus 10, and really that should be 3.72 blah blah blah, because I round that up as it's 3.715 or some crap like that. So excuse me with my language. Yeah, so on other people's calculator they get a little box coming up in the corner and you just put the minus 9.43 in there. So easy peasy. Right, what is the pH? Let's try this one. What is the pH of a 0.02 mole per decimeter solution of a diprotic acid which is completely dissociated? Now that means it's a strong acid. Remember, strong acids completely break apart. They completely dissociate. So what we're going to do, we're going to go HS, like diprotic, by the way, means 2 protons. So if it's going to fully dissociate, right, the concentration of the acid, you're going to get double the concentration of hydrogen ions. So, oh my days, what the hell is this? Yeah, so a strong acid fully dissociates. So if that is 0.02, this must be 0.04. And they will have, if you minus, oh, sorry. If you do the, oh no. Yeah, what is the pH? Yeah, so if you did the, if you minus log 0.02, you're going to get a different answer. So minus log 0.02 is going to give me 1.69, and then I'm going to go for C, and that will be wrong. So we need to go minus log 0.04 because you're doing the hydrogen ions, and that's going to give you 1.39 and give you the answer of B. Cool. Yep. It is accurate. The answer is B. Thank you, Marwa. Yeah, the answer's B. Right, what we want to do. So you need to know for diprotic acids, the hydrogen ion concentration, again, that's crusty because that silly diagram thing has that. It should have square brackets. Okay, so yeah, you get the idea. But the hydrogen ion concentration is going to be 2 times the concentration of the acid for diprotic acids like sulfuric acid. Of course, you've got triprotic acids as well. I think phosphoric acid is phosphoric acid triprotic? Yeah, H3PO4 is triprotic, so you would have to triple it with that one. Okay, so yeah, well, we've just done that. So what is the pH of 0.1 of this? So all you would do here is you go, right, well, if I've got 0.1 moles of sulfuric acid, what's the pH going to be? I'm going to have how many? I'm going to have 0.2 will be my hydrogen ion conc, will be 0.2. So I'm going to want to go minus log 0.2. And what will that give me for a pH? Anybody? What does that give me if I minus log 0.2? I don't even know. Yeah, 0.7. Thank you. 0.69, 0.70. Well done, guys. You've got it. So that's just converting in between the logs back and forth. So well done for that. Boom! Now, what we want to do is, oh my gosh, it's more of the same. We don't really need to do this because we just kind of did this, right? Yeah, we just did this. It's going to be B. Identical multiple choice question, slightly different, worded slightly differently, but the same answer, even with 1.4 in the same place. So obviously that is 0.02. It's diprotic, so it's 0.04. So you're just going to minus log. We've already done this. It's basically the same thing as before. This was a completely different question, so it just shows you the same questions come up again and again. It's going to be like 1.39, something like that. So you're going to go for B. Right, let's move on. Let's move on. Let's move on. That's Let's go. Right, let's look at weak acids. Yeah, very acidic, 0.7. That's absolutely true. Okay, to find the pH of a weak acid, you've got to use Ka. Now, if you've done equilibrium, you've done Kc. Ka, you are looking at doing the constant for acids, the weak acid constant, is going to be represented by a little equation. Let me go through. I'm talking nonsense. Let's go through what actually we need to go through. Okay, before I give you a couple of questions on it, because you might not have come across this before, so let's bash that down there. Okay, so just remember, like, a strong acid, you did this at GCSE, a strong acid, oi, what happened there? That all got a bit bogus. Oh, why is the screen gone black? It's all the technology's ganging up on me. So this happens. Oh my days. Okay, I really got to sort out my camera, man. It's just like a ghost with a glowing white head is looking at you guys. Okay, so folks, that is a strong acid. Do you guys know the definition of a weak acid? Anyone know the definition of a weak acid? That coffee tastes disgusting. Right. That's now, Matilda, that is old school. So that's old school year key stage 3. So what we're going with here is, he says, let me just zing this on here. Right. A strong acid fully dissociates in solution or in water. Okay. So it's fully going to dissociate when in solution. What that means, you can use the word ionize if you prefer. What's my my chair on? No. Okay. Yeah, fully ionizes. It fully comes apart. This means if I have 1 mole of hydrochloric acid, I have 1 mole of hydrogen ions. So nice and easy, right? You are right. It means there's going to be less hydrogen ions. Whereas a weak acid, and I'll give you the ultimate example, which they love. So a weak acid is like ethanoic acid, which you do at GCSE, and they love it the most at A level as well. They will use other examples, but this is the, like if we're going to use a salt, they use sodium chloride the most, don't they? So this is just our most common one, and it's going to look like this, and it's going to dissociate like that. But there's something I need to do, that I need to change here. I've done something intentionally wrong. So a weak acid only partially ionizes in solution. Now, what that means is slightly different. We are going to get less hydrogen ions. So pH 3.3, yeah, we'll check that out in a second. Thank you. It should be a reversible reaction. Absolutely. So what this means is, imagine you have 8 million ethanoic acid molecules. 8 million molecules floating around in a little test tube. It means if you dissolve ethanoic acid in water, what will happen is 7.9 million will remain as ethanoic acid, and only 100,000, a very small amount of the overall molecules, will break up. So what that means is that we can't treat it in the same way. We can't say the concentration, we can't say that the hydrogen ion concentration is the same as the concentration of the weak acid. Okay, which is up here. We know the concentration, if this is 0.1 moles, then this is also 0.1. So it's dead easy. If we know the conc of the acid, we can work out that. So strong acids are dead easy. It's not the same for weak acids. So we have to use this formula, which I'm just going to zing through with you. And just like all equilibria, like when you do Kc, when you use constants, or Kp, you're going to do products over reactants. So our products are, in this case, applied to this. So we can use an algebraic form, and we can use like H plus for the hydrogen ions, and instead for the ethanoate ions, we can use A minus, right? So but I could just write H plus and CH3COO minus, but that's longing it out. And then for the acid, it will be HA. And so what we can do here, cool. Now, what we have to do here is we can simplify this. Now, this is a key thing for your exams. If you're asked to write the Ka expression, you must write it in terms of what you've been given. So in this situation, I would write H plus and CH3COO minus at the top, and I would write CH3COOH at the bottom. Okay, so you must write it in terms of what they're giving you in the question. You mustn't simplify it, but the simplified version of this is Ka is equal to H plus squared. So this is really what you have to remember when solving over the acid, over HA. HA is the acid, okay? So that's the simplified version. Why can I turn that, how do I know I can turn that into H plus? Well, for every one CH3COOH that breaks down, I must have an equal amount of that and that, right? They must be equal. Mathilde, the A, okay, let me write it. So I'm going to rewrite this in terms of this. The A minus represents, when you break an acid down, that represents the negative ion, the A, and the H represents the hydrogen ion. So the A minus is this. So this would be A minus. I've just written it in, right? And that is H plus. So that is A minus, and that is HA. Okay, I technically should have written it like that, but this is the simplified version. Now, you can simplify and write H plus squared, because this concentration must be equal to that. If I have 10 molecules of that, I must have 10 hydrogen ions. I must have the same moles of each. So I know the concentrations of H plus and A minus must be the same. Okay, can you okay, so Marwa, you said, can you simplify for a weak acid that's not a buffer? So we'll look at, we can look at buffers as well. The only time you don't simplify into this over here is in the expression, if they ask you to write the expression. We'll do a question and I'll show you, okay? But then all you need to do now, see if you can do this. How would you rearrange this? How would you rearrange that to find Ka? Sorry, to find H plus. How would you rearrange that to find H plus? Ka you will be given in the question. Look, they've given us Ka down here. So it's worth knowing how to rearrange that. What you're going to do, you want to get H plus on its own, so you're going to multiply both sides by HA, which is the acid. So I'm going to go Ka. Now the acid is, so I'm just going to say Ka times the acid, or HA, equals H plus squared. And then to get rid of the square, you can square root both sides. So what you're going to do here, square root both sides, and that is, you'll get used to these. These will be like falling off a log once you've done the practice on them. So the square root of Ka times the acid gives you the hydrogen ion concentration. We don't use MR in these generally unless they give you grams of something, and there are some questions where they do that, certain buffer questions. So what you're going to do is the square root of Ka times the acid. So if we have a look at this particular question, we've been told what is the pH of this propanoic acid at 298K. The Ka is 1.3 times 10 to the minus 5. So see if you can do that. I think Marwa's already bust that out. And let me go through and I'll show you. All right, I'm going to go through and show you what we got to do here. So let me go through and show you how to do this. And then you can see if you got it right. Obviously, you're going to minus log that at the end. Right, this particular question is in terms of propanoic acid. So it's a bit long, but essentially Ka times the propanoic acid, square root that, and that equals the H+. So we want to go 0.2 times the Ka. Actually, let's write it in the correct order. So we're going to do, not that it matters, but Ka is 1.30 times 10 to the minus 5. I want to times that by, where are we? 0.02. I didn't even look properly. And then square root. What does that equal? So let's bust that in the calculator and see what we get. 1.3 times 10 to the minus 5. We're going to times that by 0.02. We get that, and then I don't know what that is. What's that? 2.6 times 10 to the minus 7, something like that. You got 3.3? Nice. Sounds good. And then just minus log to get the pH. Minus log this. So let's try that. Oh, why do I get something completely different? I'm an idiot. What have I done wrong? I think I've typed something wrong, guys. Oh, my days. Oh, yeah, that's quite easy. Yeah, I haven't square rooted the answer. That would help. So, yes. Awesome. And 3.3. So, nice. That's for the weak acid. Let's do this one. I swear it's like deja vu. It's propanoic acid. Okay. So what I want you to do, see if you can state the meaning of a weak acid and then give the expression for propanoic acid. So that's what I mean. You have to be very specific and give an expression for the acid dissociation of propanoic acid. See if you can do that. Nice. An acid that does not fully dissociate when in solution. Boom. Now you might find the expression, so you got to do the expression as well. So the expression is going to look like this. And what I'm trying to tell you is you are not allowed to simplify if they ask you to do the expression for propanoic acid. We have to write it like this. So we have to go, oh, that's disgusting. I don't want to do that. I'm going to write it like this. I'm going to use the structural formula because I don't like doing that molecular formula they've got. So there's my propanoic acid. Oh my good gosh. And all you're going to do here is do like H plus. And then you want to write your propanoate ions. So don't try and be too sophisticated and write H plus squared. There's a good chance they won't give you the mark for H plus squared because H plus squared is making an assumption. Now we assume that it makes pretty obvious if you have a pen, which I don't have, and a pen lid, and you pull them apart, you got the same amount of pens as pen lids, right? So if I pull one of these apart, these must be the same. So that's the assumption we make. And this is what will get you the mark. Don't simplify, but when you're doing the calculation, obviously you're going to simplify to H plus squared over the acid, right? I'm not going to write propanoic acid out again. It's too painful, but you're going to simplify to that. So let's see if you can oh, this one's a little bit more difficult, folks. They made this one a little bit trickier. A student dilutes 25 centimeters of 0.5 mole per decimeter propanoic acid by adding water until the total volume is 100. Calculate the pH of this diluted solution of the propanoic acid. Give your answer to 2DP. Now, you've just got to say to yourself, there's a number of ways you can do this, right? You can just look and go, but how much have they diluted? How much have they diluted it by? What do you reckon? There's a simple way, and then you can do a difficult way. So you can either use N over CV if you want to do that. You can use N over CV and prove it that way, how much they've diluted it to. What's the new concentration of the propanoic acid? So before you can work this out, you need the new concentration of the propanoic acid. And then once you have that, they're giving us the Ka up here. We're going to use this Ka here. 75 centimeters of water added, 100 to 25. Yeah, but what's the multiplier? It was 25, now it's 100. How many times weaker have we gone? They've added 75 centimeters, but this is where you might get confused. Some people will go, sir, they've added 3 lots of water. It's 3 times weaker. You've got to take the total, divide it by the original, and you'll get the multiply. So they've made it 4 times weaker. So you can just do 100 over 25. That's 4 times weaker. And then you can do 0.5 divided by 4 if you want. So the actual new concentration, as it is 4 times weaker. Now, if that doesn't make sense in your head, if you're like, nah, I don't get that, because so it's 4 times weaker. So the new conc is 0.125 mole dm minus 3. Now, some people might be like, sir, I don't get that. There is a longer way to prove that that is the new conc, if you find that difficult to stomach. But really, it's just, look, they made the volume up to 100. It was 25, so it's now 4 times more. It's 4 times weaker than it was. Okay, the volume is 4 times bigger with the same amount of moles. So you've got to think they haven't changed the number of moles. What we can do, if you like, if you don't like that and you're like, I'm not comfortable with that, you can work the original moles out. So you can say to yourself, okay, the original moles, N over CV. Let me find out how many moles were in this. So I'm going to do 0.5 times 0.025. I probably shouldn't be writing in purple. That's disgusting to see. So what is that? 0.5 times 0.025. 0.5 times 0.025. That gives me... Oh, yeah. Did I do that right? Yeah, I did. That gives me 0.0125 moles. Okay, so some people might prefer this way of working out the new concentration. This gives me 0.0125 moles. They've added water, okay? They've added water up to 100 centimeters, but they haven't added any more acid. So the moles are the same, right? The amount of particles that are floating in there of acid particles are the same. But now we're just going to rework out the concentration using a volume. We're going to go N over V if you prefer that, and we can work out the new concentration. So now we know how many moles are in the original. We just say I'm going to do 0.0125 over 100 centimeters. 100 centimeters in decimeters is basically 0.1. So I'm going to do that divided by 0.1, and that is going to give you 0.125. So it shows you. Now, we could have just simplified it by going, look, it's 4 times weaker, it's 0.125. Or you can work it out the long-ass way like this. And, yeah, both ways. So it's much easier to just take 100 divided by 4. Now we know that, guys. Calculate the pH of the propanoic acid. See if you can calculate the pH, okay? Can you get the pH based on the fact that the propanoic acid is 0.01, oh, sugar, not 0.0, based on the fact that the propanoic acid is 0.125 mole DM minus 3. No, they said they added water, keyword there, until the volume's 100. So they didn't say they added 100 to 25, they added the volume until 100. So total volume's 100. So you've got to be careful with the wording. They didn't go to 125, just to 100. So our new concentration is 0.125 mole per decimeter of propanoic acid. So see if you can calculate the conc now. Well, not the concentration, we've done that. Calculate the pH of a weak acid, and you're going to want to use this is the Ka, and this is the conc of the acid, and you want to basically rearrange that equation and see if you can get the pH, guys. Nice. It's always good to have a challenge.
Say when.
Round one.
Let's go! Okay, oh my days, I just seen my screen is like hanging off the side of things. Oh, I do need to sort it out. I've got a new desk over there with a plant next to it and everything. Oh, lovely. Yeah, anyway, I do need to sort out my setup for these lives. It's proper crusty. Right. But, you know, I'm all about the teaching. Is it the moles of the dilute in the minus log? So, no, you want the conc. So if I rub all this out, because this is all probably a bit confusing, let's rub all of this business out. So that was just two ways to get to the same answer. You can just say, if you got 25 centimeters or something, can you make it to 100? You've made it 4 times weaker, right? So the new concentration is 0.125. It was 0.5. 0.5 divided by 4 is 0.125, so they've made it 4 times weaker because they went from 25, they added 75 centimeters of water. I know what you're thinking, but they've added 3 times the water. Why isn't it 3 times weaker? But the total volume has gone to 100. So overall, it's 4 times weaker, 100 divided by 25. So the new concentration is 0.125. That is the acid concentration. So the new propanoic acid concentration is 0.125. So we want to say, so using that, propanoic acid is 0.125, and that's mole DM minus 3. And I'll just write the KW so you can have them all in the same place, but it's in the top part of this question because these were both parts of the same question. So 1.35 times 10 to the minus 5 is the Ka, not KW. I don't know what I'm waffling about. And why does that come out in caps? You twits. At this particular temperature. And you've got a pH of 2.9. Sounds good. That sounds like an acid. Sounds like an acid. And 2 DP. Well, let me have a little. Sounds pretty good. So what you want to do is you want to go 1.35 times 10 to the minus 5. Let's double check that if anyone else can work that out. And then you're going to have 0.125, and that is going to be squared. And we're going to divide that. Oh, I'm talking out my backside, aren't I? That's H plus, sorry. And that is over 0.125. So we want to rearrange that and make H the subject. So what we're going to do is going to multiply each side by 0.125. That gets rid of the 0.125 under there. So we multiply both sides by 0.125, gets rid of that. And then we have 1.35 times 10 to the minus 5 times by, oh my gosh. 0.125. Leave my tongue stuck out there. And then we want to square root both sides to get rid of the square. So if I square root that, gets rid of the square. And then basically I want to square root that. And then we're going to minus, once we get h plus, you want to minus log, bash your h plus in. And there's your answer. Anyone else get 2.9? Let's have a little look. Let's smash it in. So we go 1.35 times 10 to the minus 5 times that by 0.125 equals that. Square root answer equals that. Minus log answer equals, yeah, I got 2.887, maybe 2.89. I think they're going to be, I got 2.887, and I would round that to 2.89 as they want 2dp. I go 2.89. Yeah, cool. Right, I'm going to put the answers up. So here we go. Yeah, 2.89 must be to 2dp. So there you go. That is hopefully messy. Right, let's just do a couple more of these. What's the time? Okay, we've got 20 minutes. I might do a couple on buffers and stuff as well. Let's do, I might do a buffer question. But I'm going to do buffers. I know I need to do really a whole hour on buffers and stuff like that. And these are just calculations. There's a lot of theory to go with acids as well. So I'm just kind of doing calculations today. Nice one. So, trichlorophenol, don't worry about the 2,4,6 trichlorophenol, it's just a name, is a weak monoprotic acid. So look, they're being nice, they're telling us it's monoprotic, 1 hydrogen ion per molecule. So its Ka is 2.51 times 10 to the minus 8. Oy! What is the concentration in moles per decimeter of hydrogen ions in a 2 times 10 to the minus 3 mole per decimeter solution of 2,4,6 trichlorophenol at 298 K? They're not asking for pH. So this is just one of them nice little multiple choice questions they bust out. So see if you can work this out. Have a go. And if you're watching the live, we don't have many people, but we keep going. We're going to do an hour. Remember, I'm here every single Monday. So, and you can ask me questions about other topics you're doing if you're stuck on something or there's something you don't understand. Like, because we're kind of like done pH calculations and weak acids. I could go for a buffer if you want me to go for a buffer, or we could just continue with a few weak acid examples. Right. See if you can. How many hydrogen ions are in a 2 times 10 to the minus 3 mole per decimeter of this? So all you got to do here is write out your expression. Ka is equal to H plus squared over the acid. And they don't want you to do the minus log bit. They just want you to find out the hydrogen ion concentration. You go in B, Marwa. Let's have a little look. Oh my good gosh. So 2.51 times 10 to the minus 8. So what you're going to do, you're going to times the Ka by the acid, same as always. So you can kind of get into the routine of knowing exactly what to do. Square root of that. When you have a weak acid, you'll kind of get into the practice, so you don't even have to write any of this out, and you'll be able to bust it out. Yeah, this is AQA. Yeah, and also it's working out the pH or the concentration of hydrogen ions in a weak acid, or the pH of a weak acid, is the same for all exam boards. But yeah, specifically, this was taken from AQA. So I want to do 2.51, which times 10 to the minus 8 is the acid dissociation constant, the Ka, and I want to times that by the conc of the acid. Now it tells me the acid is monoprotic, so I can just write that concentration in. I don't need to do anything funky with that concentration, like multiply it. And I get 5.02 times 10 to the minus 11, which is A, but I haven't yet square rooted it. So you can see what they do, which is clever. I've just times the Ka by the acid concentration. I don't know if you probably can't see that there, but I've just times the Ka by the acid concentration, and straight away it comes up on my calculator one of the answers. So they're trying to trick you, and then I'm going to square root that answer, and that is going to give me B, basically 0.0000709. Yeah, it's going to give me B. So the correct answer is B. But on the way to B, they gave us A. So that's just a typical little exam board technique to try and trick you while you're halfway through your calculation. And that's why multiple choice questions are actually really unforgiving, because someone who got A, you know that they've at least times the Ka by the acid. They've done a step, right, in solving the problem, but they get no reward for that. They just get a wrong answer. So let's have a little look. Have I got another Ka, or do I want to go on to some buffage? Oh, have people done Kw? Have people done water before? So we have another constant. Maybe I shouldn't do Kw. Why do I feel like my chair's on something? It's not my foot, so don't really matter. But hey, I might as well do. I'm going to quickly rinse through Kw then, and then I might do a quick buffer calculation as well. Okay, so yeah, I'll do a really difficult one on acids and bases in a sec. Yeah. So I'll put up a hard one in 2 minutes. This is a question about water. An equation for the ionization of water is H2O goes to H plus OH minus. You have to know this. Now, the expression for the ionic product of water is Kw equals H plus times OH minus concentrations. The value of Kw at 310 is 2.4 times 10 to the minus 14. Calculate the pH of water at 310. Now, this is an important point. People think, what is the pH of water? And everyone will say, oh, it's pH 7. That's nonsense. It depends on the temperature. So the pH of water, pure water is only made of hydrogen ions and hydroxide ions. Pure water's pH depends on the temperature, and therefore Kw, right? So Kw is different at different temperatures. So when we say water is neutral of any solution, whether it's water or another solution, neutral means you have the same amount of hydrogen ions as hydroxide ions. It doesn't mean the pH is 7. So that's something we have to get out of our head at A level. Something can be neutral at 5.36. Okay? If it has the same amount of hydrogen ions as hydroxide ions, it's neutral. Okie dokie. Anyone solve this one? So what we want to do here, calculate the pH of water at 310. Well, we can make an assumption. Think about it, guys. For every H2O that breaks down, you're going to have one lot of H plus and one lot of OH minus. We can do the same thing that we did with the Ka. We can assume that Kw, when water is pure, we're dealing with pure water. There's no salt in this. There's nothing else. They should have said in the question, this question is about pure water, but never mind. We can assume when we're dealing with pure water that Kw is equal to H plus squared. So now you can calculate its pH by rearranging that. So see if you can calculate the pH, guys, by rearranging that question. What would the pH be? I probably shouldn't write in pink. That's pretty disgusting. But essentially, it's trying to tell you here the expression, yeah, blah, 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 dee-dee-dee, da-da-da. Cool. So what I want to do, I want to find the H plus. I want to isolate it on its own. So you should get used to doing this. Kw, the square root of Kw is equal to H plus. Why do I square root Kw? I want to square to get rid of that little to the power of 2, and then I have to square both sides. So the square root of this is going to give me the hydrogen ion concentration. So let's go ahead and do that and see if you can work out the pH. And it's water, right? And we know roughly the pH is going to be 7. So that's what I'm looking for. Something, when I get to my answer, I'm looking for something that's in that ballpark. You know, I don't want something that's telling me it's 1.5. So if I square root that and then I go minus log answer, I'm going to get, lovely, nice one. You're spot on there. Pops in, absolutely. So I got 6.80989, and then of course we'll go round that up to 6.81. Absolutement. Yes. 6.81. Awesome. Well done. Yes. Yeah, there you go. Okay. Nice. So that's KW for you. Now, there are some KW calculations, guys. Not all the KW calculations are like this. Sometimes, or quite often, the KW, the H plus and the OH minus aren't equal. And it might be a situation where they say sodium chloride or something is dissolved in water. They give us the KW or sodium hydroxide, sorry, is dissolved. And we can work out what the OH minus is. If of a strong base, you can use KW to work out the pH of a strong base. Let me see if I got a KW with a strong base. Now that's just another. This is another example of working out pure water, so it's the exact same thing. This is another one of what I've just done. This is exact same thing of what we've just done. So it's just showing you, look, Kc is equal to that, like acid, base, whatever. Explain why H2O is not shown in the expression. All right, so they're kind of saying, well, it's the constant for water, but we don't bother showing H2O. Why do we not divide by H2O? Why is Kw just equal to hydrogen ions times OH minus? What could that tell us about the amount of H2O in the equation? So, then it says, give the expression, calculate the pH of water at 50. So at each one of these temperatures, the pH of water would be different. And this is pure water, so this is neutral, right? Pure water is neutral, has the same amount of hydrogen ions as OH minus ions. Yeah. So what we're going to do here is go, if we work this out, we want to use that as the KW. Who can work this out? So how could one draw the hydrogen bonding on a diagram, and could you briefly overview the bonding? Yeah, so I'll do that while you guys work this out, what the pH is, and then I'll show you the answer to that. I'll very quickly answer your question here. Let me just, so water looks like this. I definitely did a live recently on this, sometime back a little bit, on polarization and intermolecular forces. So what we do, and now in AQA you don't actually have to show this, or actually maybe you do, but not in AQA biology you don't, but maybe not. I don't know if in chemistry, I don't think they actually penalize you in AQA for the delta sign, but this is slightly positive, slightly negative, slightly positive, due to the electronegativity of oxygen being far greater than hydrogen on the Pauling scale. It means that the electrons are in the bond that pull towards the oxygen, making it slightly negative. What this means is, and you have to be very careful with your wording, is that an adjacent water molecule or a neighboring water molecule, you mustn't say the elements in the same water molecule. So you don't want to say delta negative oxygen hydrogen bonds to a delta positive hydrogen in the same water. That's not true. This is a covalent bond. This black line is a strong covalent bond. So this delta positive hydrogen on one water molecule bonds, and we use a dashed line, to the delta negative oxygen on an adjacent or neighboring water molecule, on another separate water molecule. You must make it clear that the hydrogen bond is in between two separate water molecules. Delta negative oxygen, hydrogen bonded to delta positive hydrogen. Now, Um, yes, water could hydrogen bond to ethanol. Absolutely. And the small alcohols like ethanol will dissolve easily in water. So ethanol, if you shake some vodka and water, you're not going to get layers or anything like that. The water and the vodka, you're going to shake it together and you're going to get dilute vodka. So yes, you can shake alcohol with water. The small alcohols, the longer the carbon chain of the alcohol, the less soluble they get. So if you had hexanol, because it has a large bit which has no O and H on it, and it just has an OH at one end, and then a big part of the molecule doesn't have an O and NH, that part of the molecule cannot hydrogen bond to water, so it becomes less soluble the longer the chain. Because those parts of the molecule can only do van der Waals forces with water, and water's like, no, I'm going to stick where I am, bonded to this water molecule. Essentially, when something dissolves in water, it has to be energetically, like, it has to be reasonable for the water to form a hydrogen bond with that instead of maintaining its hydrogen bond with another water. So it has to be equally as attractive to the water. Like, oh, now the water's not going to give up bonding to this to bond to a carbon chain. It's just going to be like, no, why would I do that? That's makes me energetically unstable. So yeah. Am I frozen? I don't know. Has the live frozen up? I'm not sure. Oh, entropy. A little bit. It's kind of enthalpy, entropy. It's all to do with how exothermic, whether the energy change is exothermic or equal, roughly equal. Yeah, it's kind of like enthalpy or solubility. Okay. Anywho, that's how you draw a hydrogen bond. Right, 6.3. 6.3 sounds good to me. Who come up with 6.3? I'm going to give you a boom, I think, because I've got the marks here. Ba, ba, ba. Oh, this don't look like it's the right mark scheme for this business. What is this? Oh, no. There we go. Have I even got the answer on here? Oh, yeah, 6.63. Yeah, 6.63 will get you all of the marks. I don't know if you can see that there because I've gone and written it. Oh, yeah, it can. That'll override all of that. Yeah. So it'll be 6.63. So well done. Yeah, 6.63. Nice. It says, explain why water is neutral at 50 degrees. So what they're saying is, how is water neutral even though the pH is 6.63? Because it's not to do with what you were taught in year 7, 8, 9, 10 and 11. pH 7 is not when things are neutral. Things are neutral when the hydrogen ion and hydroxide ion concentration are equal in water. So that's not necessarily at pH 7. We just simplify it to say water's pH is 7. But that all depends. Maybe at 20 degrees, if we carried this out at 20 degrees or 25, it's going to be, oh yeah, at 25, 1 times 10 to the minus 14, I think it's going to come out as pH 7. So at 25 degrees, it'll be pH 7. Yeah. So I think the reason we say pH 7 is probably at 25 degrees. If I do 1 times 10 to the minus 14, then, like, yeah, that's going to be pH 7, isn't it? Na, na, na. Oh, my days. Yeah, so if you did water at 25 degrees, it would be pH 7, would be neutral, but it's still neutral at these other temperatures. Okay, let's zing, zang, zong. See if you can solve this one. This is another KW. And then I'm going to put up a hard one. Somebody wanted a hard one. Let me put up a hard one for you. I'll just do one hard one before I sign off because it's just a little quick live on the old acids and stuff. Oh, I know what I want to ask. What would you say is the hardest topic you've done so far in A-level chemistry. What's the hardest topic, or the one you're most confused about, or part of a topic? So you might not find working out pH hard, but you might find weak acids hard, or you might not find certain things hard. You might not find isomers hard, but you might find EZ isomerism hard, or something like that. So what would you say? Oxidation numbers in redox. Yeah, quite a few people don't like that. Buffers. Yeah, Marwa, buffers are quite hard. I'll do a buffer question next, but I probably should devote a whole live to buffers because I need to go through the theory of buffers. So, my eyes are so bad. All right, Poppy Shin, let's have a little look. What is the concentration of sodium hydroxide in moles per decimeter? The hardest thing we have is electrode potentials. Yeah. Yeah, electrode potential cells is hard. The application, the exam questions on that, I would say are very hard for AQA. If you do AQA, the electrochemical cells is a lot harder than in OCR, but then OCR has topics that are harder than AQA. So it's like mix and match. Certain topics are really hard. Like acids and bases are kind of easy in AQA. Acids is very easy, but in other exam boards, the acids topic is a bit harder because they do strong and weak bases and things like that. Yeah, the application of electrode potentials is a bit nuts. I'll probably do a live on that then at some point if people want to do that. But it's a bit early in the year. Like a lot of people won't have covered that yet. They won't cover that till closer to Christmas probably, or after Christmas. So because that's kind of like one of the things schools leave to the end. I would say that and complex ions are the hardest according to me. But complex ions is mainly just because it's loads and loads of memory recall with no kind of like skills. It's just a lot of memory recall of color changes and things, and it's something that most people want to avoid doing, and schools do it right at the end of the A2 course. They put that right at the end and people are just like, oh, complex ions, you know, they don't want to go through and memorize all the color changes and all of that business. Right, which is the concentration of sodium hydroxide in moles per decimeter? Okay, so we know that Kw is 1 times 10 to the minus 14. Oh, and it has a pH of 14.30. So what we know is that Kw is equal to H plus. So this is one where it's slightly different. You're working out the OH minus conc. So essentially they're saying 1 times 10 to the minus 14 is equal to... Oh yeah, we need to minus log this bad boy and work out the hydrogen ion concentration. So let's minus log 14. Oh no, what am I doing? Not minus log. Shift log minus 14.30. And that gives me, okay, so my hydrogen ion concentration is 5.01187. Oh my gosh, stop there. Times 10 to the minus 15, so times OH minus. What are you going with here, guys? So is it just 1 times 10 to the minus 14 divided by 5 times 10 to the minus 15? That's what I'm thinking. Oh my gosh, what's wrong with me? I think I've done this wrong. No, it's right. Okay, yeah. So if you do 1 times 10, you're right. Well done. Ugh, that's terrible, isn't it? Over equals OH minus, and that is 2. So D is the correct answer. Well done. Yeah. You're right. You got it absolutely spot on. Boom. Now you got it right. You smashed it. Okay. Oh, I'm not going to do that. No, I'm not going to do that. Not going to do that. Not going to do that. Let's move on. What's that? Oh, here's a buffer question. Okay, this is a dead easy buffer question, but we might as well. Okay, so I'm just going to do a really hard buffer question. This is not the really hard buffer question, but I'm going to do a really hard buffer question. Just quickly, does everyone in the chat there know what a buffer is? Do you know what a buffer is? I don't know if you've done buffers. Has everyone had a go at buffers yet before? See, I probably should do a whole live on buffers, but like, obviously, I'm not going to go through all the buffers now and the theories behind it, because it's just a long to do now. I ain't got enough time, but I've got time. Yes, yes, yeah, yes. A weak acid, and you might want a strong base. You, She done buffers. I like import on 45. You're right. A buffer resists the change in pH. Well done. When a small amount of acid or alkali is added. Perfectamungo. So what you want to do here, what did you say? The pH, you've already worked that out, 4.28. So solution O should be nice and easy, right? Now, buffers have a different, I just wanted to get down to this, right? If you rearrange, this is what I do to solve buffers. Now, I'm not saying we use this now, but the hydrogen ion concentration of a buffer, this is what I do, and I ain't got time to go through why I do this, but is right, I do the acid over the salt. Now I know what you're thinking, what the hell you want about a salt? Normally if I want to make an acidic, normally if I want to make a buffer, I'm going to use a weak acid and a salt of that weak acid. Okay. Oh, you got a practical on serial you're doing serial dilutions tomorrow. Well, if you're doing serial dilutions, then you need to know the difference. So see if you can rearrange, see if you can rearrange that to find the hydrogen ion concentration and then minus log the H plus. And you just want to do the acid over the salt of the acid. You can see I've got ethanoic acid, and that's sodium ethanoate. So I want to do 0.3 divided by 0.1 times 1.75 times 10 to the minus 5, and then minus log the answer. Now, whoa. Yeah, you can use anyway. I prefer this equation. I prefer this equation for doing the buffers. Oh, it's 5.25 apparently. No, it's not 5.25. You're right. You're right. You're right. You're right. You're right. You're right. It is 4.3. Did you get 4.3, 4.28, or 4.3? Let me just quickly bust it out in my calculator. So you want to do 1.75 times 10 to the minus 5. So 0.3 over 1 is 3. So I'm just going to do 3 times 1.75 times 10 to the minus. I don't think I've got all of the marks on the mark scheme there. So I haven't got the actual. Hold on. Right. 1.75 times 10 to the minus 5 times 3 equals that. Then I want to go minus log answer equals, yeah, you're right, 4.279. Yes. So 4.28, 4.279. You're absolutely right. That's going to push that up to 4.28. That's what you should get for that. Nice. Right, let me give you a dirty buffer calculation then. 6 marks. This one's a disgusting 6 marker. Now, oh, hold on. Who said they're doing dilutions tomorrow? Was that Matilde? So you're doing dilutions tomorrow. What type of dilutions? Yeah, I just rearranged that. Oh, you're doing cereal dilutions. For potatoes. Are you doing the potato tubers? For bio? Well, it's not too bad. There's actually cereal. I always get them mixed up, right? In biology, you've got dilution series and you've got cereal dilutions. So I think cereal dilutions is the one where you have 10 centimeters. It depends whether they're going to give you percentage starch or mole per decimeter of starch. So it depends if they're going to give you percentage starch solution or whatever. So, or milligrams or whatever they're going to give you as your unit. Well, like if they give you 1 mole per decimeter, if they give you your 100% starch, you just put 10 centimeters in a test tube, and then you're going to transfer. It depends how much you want to dilute it by. So if you want to half it each time, you just have you start with 10 centimeters in a test tube. You take 5 out from there and add 5 of water. That's now 50% the strength of the original. You then take 5 out of that one, put it in the next one, and add 5 of water, and that's now half again. So with each test tube, you're halving the concentration, and you're going to end up with like 5 test tubes, all with 5 centimeter cubed in each. So you might be doing that one. Okay. Let me just zing this one. Did you, Poppy Shin, did you do, and I haven't checked, I haven't worked through it yet. Did you change the acid as well? Remember, the acid, the moles of acid have gone down. So if you're going to increase the moles of the salt, make sure you decrease the acid by the same amount you increase the moles of the salt. So, how we do this, I'll go through, but you guys obviously are probably, if you ain't done buffers, you might find this hard, but a student prepared a buffer solution by adding 0.16 moles of a salt, Kx, to 100 centimeter of 0.5 mole of weak acid, HX, and mixing thoroughly. So what you got to understand is a weak acid makes a crap buffer on its own. And the reason being, HX is algebraic, right? The H stands for the hydrogen ion, the X. So this could be ethanoic acid. The X would therefore be CH3, COO minus, and the H would be H plus. That would be ethanoic acid. It's a weak acid. So if you just had this weak acid as a buffer, yeah, nice. All right. Then I think your calculation's probably right. I will check it now. If you just have a weak acid as a buffer like that, that is a crap buffer because it has lots of weak acid, it can take out any alkali you add, but it can't take out acid. If you add acid to this solution, this can't take out acid. So I need some sort of base of the weak acid, and I'm going to get that by using a salt. Now the salt Kx, right, is going to be almost 100% soluble. So we're not going to use a reversible symbol. That's a crap color to do, isn't it? What shows up? Maybe yellow. Yellow and blue. That's probably repulsive as well. Right. So if I was to do Kx, Kx is going to fully dissociate. We don't have to worry about the potassium ions. They're going to do bugger all. But it's going to give me loads of the salt. Is going to give me loads of, like, if this was ethanoic acid, give me loads of ethanoate ions. So now, if you add an acid, I can take it out with X minus, and it's gone, neutralized. If you add a base, I can take it out with HX, gone, neutralized. So the pH doesn't change much. Now, we haven't been asked to calculate the original pH of this solution, but we have been told that we had 0.0136 of a salt, 0.0136, of salt to 100 centimeters of weak acid and mixing thoroughly. The student then added potassium hydroxide. So we had 0.0136 of a salt. That means I've got 0.0136 moles of X minus. Why? Because this fully dissociates. Now my acid is 0.5 times 0.1. That is actually 0.1. 100 centimeters, remember, is 0.1 dm. If I do 0.1 dm times that, I'm going to get 0.05. So I've got 0.05 of the acid. Even though some of it has dissociated, we're going to make the assumption that so few has dissociated. My acid is still 0.05. Now someone has added alkali. Little pains in the butt. They've added 3 times 10 to the minus 4. So they've added 3 times 10 to the minus 4. So some of my acid is going to disappear. It's going to be neutralized by that hydroxide ions. It's going to neutralize that because that's how it works as a buffer. So how much acid do I have left over? I'm going to go 0.05, take away 3 times 10 to the minus 4. And I think I'm going to be left with 0.0497. Oh shit, is that right? Excuse me. Let me just, I actually have to do this on the calculator. 3 times 10 to the minus 4 equals 0.0497. So that's how much acid we have left, because some of it got neutralized. So that's how much of my HX I have left. Sometimes they use HA, sometimes HX. Now, what did happen is that I need to increase this. I need to add this to 3 times 10 to the minus 14, to the minus 4, sorry. And that is going to equal 0.039. And so that's the difficult bit with buffers, is that after you add an acid or alkali, you have to, if you add an alkali, your salt is going to go up and your acid is going to go down. If you add an acid, your acid's going to go up and your salt is going to go down by a certain amount. So, and now all we've got to do is acid over the salt times the Ka. I know, pain in the butt, but there we go. Acid divided by salt. So, do I need to change this into concentration? No, because it's in 100 centimeters. So it's a ratio. If I divide them by 0.1 and still time, it's a ratio basically, so I don't need to worry about that business. So hopefully that is all good. And is it going to be 3.3? I don't know. Let me have a go. So what is it? 0.0497 divided by 0.0139. Bish bash bosh. Okay, that gives me 3.57. I'm then going to times that. Did they give us the Ka? Yes. 1.41 times 10 to the minus 5. And that gives me 5.04 times 10 to the minus 5. And then what I want to do is minus log answer 4.29. Yeah, I got 4.29. I got 4.29. Anyone else get that? No, that's a good explanation about how it shifts to the right-hand side. All right, see you later, Mathilde. That's a good explanation. There's 2 ways that you can, if you're asked to, if you're asked to sort of verbalize, not verbalize because you're writing in your exam, if you're asked to sort of put the theoretical reason of how a buffer works, there are 2 ways. I always stick to this basic way of, oh, if you add an alkali, it will be neutralized by the acid, and if you add an acid, it will be neutralized by basically the salt of the acid or the base. But you can talk about it in terms of equilibria as well. So you can talk about the shifts in terms of equilibria as well. I think it's 4.3. I think it's 4.29, so round up to 4.30, I think. So I think it's 0.0497 over 0.0139, and then times by 1.41 times 10 to the minus 5, and then minus log that. And then I think I might finish there. I'll probably do a lesson on buffers. But yeah, you're right. You said cause OH minus reacts to OH plus. Yeah, 4.3, cool. Yeah, OH minus reacts to H plus forming water. So yeah, if you add hydroxide, forms H plus forming water. So in order to counteract the decrease in H plus ions, yeah, you can do that. You can say that. Absolutely. When you add, that's another really good way of explaining it. If you add the potassium hydroxide, then it uses up these H plus ions. What do we know about Le Chatelier's principle? More of the acid breaks down to try and counter the change. And so your acid goes down and your X minus, it's not really your salt, but you know what I mean. It's the, oh God, I'm not going to even say it right. It's the like the because we're dealing with weak acids, it's essentially going to be the propanoate or ethanoate ions. You're going to get more of those. You're absolutely right. So that's a really good way of explaining it. Talking about the shift in equilibria. So essentially X minus is going to increase by the amount of acid that broke down. I think I will probably finish there, guys. I could do another buffer. I don't think I want to do another buffer. Let's allow the buffers. I've got hundreds of buffer questions. I'm going to leave it there, guys. It was just a quick one on calculating pH and stuff for an hour. I know you guys are probably busy at this time coming into December and all of that. So I'm going to keep up with the lives anyway. They tend to get busier after Christmas as it goes towards the exam. So, yeah. But Thursday, I am doing a bio one on Thursday, and I can't even remember what I put up. I put up a little poll for that. I might do aerobic respiration, so Krebs cycle, oxidative phosphorylation, or I put some other ones up. I think protein synthesis, that's pretty easy. I was going to do structure of proteins. I was trying to think of some other ones to put up. Oh, fish and insects, exchange surfaces for fish and insects, trachea, tracheoles, all of that, rhythmic abdominal movements, all of that business. So it all depends. Have a good one, guys, and take care. And I've got a walkthrough of the A-Level AQA Paper 1 2024 out at the moment. You might want to check it out. And next week should take me about... I'll probably put a walkthrough for the Paper 2 and Paper 3 out before December. So as well. For the 2024s, I'm not allowed to do the 2025s. It's kind of like... You're not allowed to, so, you know what I mean? I'll get kicked off of YouTube if I did those because those haven't been published. They're not open to the public yet. Alright. I did mass transport in plants last week. So, I did a live last week. So, I did mass transport in plants last week. Like phloem and active loading and all of that. I did that on Thursday last week. So, you could have a watch of that if any of that's interesting. There are bits, biology is like 90% of, is that for me, Waleed? Biology about 90% do off the top of my head. So you could sort of say, oh sir, can you go over that, go over that. There's always one or two things that don't stick. There's like certain names of people in your life. You can never remember someone's name, or you get two people's names always mixed up. You call someone Steve and someone Dave, and you just can't ever get over that. There's like that with me with biology. There's a couple of things where if I'm going to teach it, I have to have a look at it beforehand. With chemistry, I would say like electropotentials, I have to have a quick look at it. I could teach it now because I just did it the other day. I was teaching someone the other day electropotentials. But if I leave electropotentials for a year and I haven't looked at it in a year, something's going to go out my head, just a little part of it. And the same with complex ions. I'll forget the different colours and stuff. So yeah, I know like 90% of them off by heart just from teaching it. But there's always something that doesn't stick in my head. And then moving between the different specs. So if you're doing OCR, then you have to know about conjugate bases and you have to know about the conjugates. If you're doing AQA, you don't need to know about them. So I'll get into a habit of just teaching and looking at AQA work, and then I get loose on that, or on like something from OCR. So, but yeah, it's definitely not because I'm clever. It's just because I've 25 years of doing A-level chem and bio. I mean, I do a bit of physics, but I just haven't done the physics anywhere near enough. So like physics, I know about 20% of the A-level course off by heart. So people say to me, "Oh, sir, can you do some physics A-level stuff?" And I'm like, "No, I'd have to sit before every time I go live. I'd have to sit for 3 hours and like read up on it and all that. I haven't got that kind of time. Whereas with biology and chemistry, I can just do any topic really without any practice." Anywho, peeps, have a good one, and I will see you later. Yeah, if you want to do the mass transport in plants, you could check out my live. I did one last week on that, and yeah, like I say, I've got some A-level papers coming out. Take care. All right, cool. And if there's any topics you or little things you want me to explain, I can go over them. Like I said, I know 90% of it off by heart, so you can just ask me it during any live. You can say, "Sir, can you explain this?" And I can explain it because 90% I'll be able to. All right, enough of my waffle. I'll see you guys later.
You're still here?